Hello, my name is Vikran Jain, and this is my video presentation for Lab 3 of Physics 2211. In this lab, I shall explore the application of Newton's second law, momentum, and Newton's laws of universal gravitation in a situation involving a star orbiting around a black hole. The purpose of this lab was to create a computational model of the star's motion using those three components and to analyze how a change in any of these factors would impact finding the mass of the black hole. As we shall later see, there is a significant conceptual difference between Fnet and dp/dt, as well as their parallel and perpendicular components. As the orbit of a star around a black hole was examined in this lab, the system was set as the star. The position versus time data points from the star's orbit, which was given from a CSV file, and the momentum principle, as well as the equations derived from that principle to calculate the mass of the black hole, were involved. First, let us note the equations tied to the primary concepts involved in this lab. First of all, of course, is Newton's second law, which is shown here as V final equals V initial plus Fnet over mass times delta T. Fnet itself is shown as dp/dt. It can also be defined as the sum of Fnet parallel and Fnet perpendicular. Similarly, dp/dt can be defined as the sum of its parallel and perpendicular components as shown. Momentum, or P, is shown to be the product of mass and change in velocity. Also, change in velocity can also be referred to as delta V. Now let's take a deeper look at its perpendicular component, which is equal to mv squared over r. This is a significant point to note because of the circular/elliptical motion of the star around the black hole, which thus involves an application of the concept of centripetal force. However, perhaps the most important formula to be aware of for this lab is the magnitude of Fnet being equal to the universal gravitational constant, which is 6.6 times 10 to the negative 11 times the product of two masses, which in this case would be those of the star and the black hole, divided by r squared. This formula refers to Newton's law of universal gravitation. This lab was very heavy on computational modeling because the data that we were using in the lab was already given to us, so no physical experiment was needed. So first, let's analyze the system properties and the initial properties of the lab in terms of the Python code. The mass of the star was given as 1.9890 times 10 to the 30th. And this mass was given in kilograms, and the position of the black hole was given in vector form of negative 3.00 e to the 10th as the x component, 4.00 e to the positive 10th as the y component, and 0 for the z position. This vector was really key in terms of finding the position of the black hole, and helped us refer to where the relative position of the star was as it was orbiting around it. As you can see, delta t was given as 86,400 seconds, which was the time step, and the t of the first observation was t equals 0. Although the delta x and x vel of the index was given in star code correctly as the one as you can see right here, delta y needed to be manipulated, as well as y vel of the index, and because delta y had to not be 0 or whatever the initial condition was set as, but instead be y of index plus 1 minus y of index, and y vel index was set to be delta y over delta t. This was very key in terms of computing the y component of the velocity. As you shall see, the theme of manipulating code and using Python code to create an accurate computational model carries on throughout the rest of this Python code. The first example of that will be shown for p initial, which was set at and can be referred to as star.m times initial velocity, and p final was set as star of the mass of the star times final velocity. dp/dt was set as the change in momentum divided by the change in time, and Fnet was set equal to this dp/d value. Here you shall see a key component of the Python code in dmag_p_dt equals magnitude of final velocity minus the magnitude of the initial velocity divided by time. Also, dp/dt in terms of the parallel component was set equal to dmag_p_dt times p hat. This is key because the parallel component of momentum, change in momentum, refers to the magnitude of the movement. and change, while the perpendicular component refers to the change in direction. The most important part of the code was shown in the portion that calculated the mass of the black hole, with the change in distance variable being equal to the position of the star minus the origin of the star. The origin position was set as the position of the black hole. G, which was a universal gravitational constant, was set as 6.6 e to the negative 11, and the black hole mass was equal to the magnitude of F net times magnitude of change in distance to the second power and divided by G times star dot m. When the code is run, you can see the movement of the star around and during its orbit around the black hole, and the three arrows show the different components of its movement. The black arrow is the parallel component, and the blue arrow is the perpendicular component of its movement and momentum. Upon its being run, the code showed that the mass of the black hole was 2.212 times 10 to the 31st kilograms. Although the code shows dp dt equals F net, dp dt equals F net is derived from the momentum principle and can be calculated from observed data. However, F net is the force causing the position and momentum change, which cannot be measured directly. So F net represents more of the qualitative aspect of the data, while dp dt refers to more of the quantitative aspect. Even if the black hole involved in this solution was replaced with a different one, the mass of the new black hole would not be able to be calculated because the law of universal gravitation would show the same values used, and so the mass of the black hole, which would be the second mass involved, would still be remaining the same, and thus a new mass would not be able to be found. This concludes my discussion for Lab 3. Thank you for watching. I appreciate it.